Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine generalized constants A, B, C and D of a three-phase medium length transmission line based on its nominal T equivalent circuit when values of transmission line parameters are given. We shall also learn how to compute percentage voltage regulation of this line using those constants when load details are given. A balanced three-phase load of 30 megawatts is supplied at 132 kilovolts, 50 Hz and 0.85 power factor lagging by means of a transmission line. The series impedance of a single conductor is 20 plus J times 52 ohm and phase to neutral admittance is 315 micromho. Using nominal T method, we have to determine the ABCD constants, the sending end voltage and the percentage voltage regulation. Let us first write down the given data. Power delivered to the load PL equals to 30 megawatts, that is equal to 30 into 10 to the power 6 watts. Line to line receiving end voltage VR line equals to 132 kilovolts, that is equal to 132 into 10 to the power 3 volts. For star connected system, receiving end voltage per phase VR equals to VR line divided by root 3, that is equal to 132 into 10 to the power 3 divided by root 3, that gives us 76,210 volts. Given load power factor cos phi L equals to 0.85 lagging. Let us now determine power factor angle. Phi L equals to cos inverse 0.85, that is equal to 31.7883 degree. Expression for power delivered to the load PL equals to root 3 times VR line into IL cos phi L. Therefore, load current IL equals to PL divided by root 3 times VR line into cos phi L. Using values we get 30 into 10 to the power 6 divided by root 3 into 132 into 10 to the power 3 into 0.85. That gives us 154.372 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 154.372 ampere at an angle minus 31.7883 degree. In this case, load current IL equals to receiving end current IR. Given series impedance per phase of the transmission line Z equals to R plus JXL equals to 20 plus J times 52 ohm. This may be written in polar form as 55.7 ohm at an angle 68.9625 degree, and shunt admittance per phase Y equals to J times PC equals to 0 plus J times 315 micromho. This may be written in polar form as 315 into 10 to the power minus 6 mho at an angle 90 degree. Let us now calculate Y into Z. Using values we get 315 into 10 to the power minus 6 at an angle 90 degree into 55.7 at an angle 68.9625 degree that gives us 0.0175455 at an angle 158.9625 degree. This may be written in Cartesian form as minus 0.016376 plus j times 0.0063. Now we shall calculate 1 plus 1/4 of y into z, that is equal to 0.995906 plus j times 0.001575. This may be written in polar form as 0.9959073 at an angle 0.09061 degree. For nominal T equivalent circuit, A equals to D equals to 1 plus half of y into z, that is equal to 0.991812 plus j times 0.00315. This may be written in polar form as 0.998125 at an angle 0.1808 degree. B equals to z into 1 plus 1/4 of y into z. Using values we get 55.7 at an angle 68.9625 degree into 0.9959073 at an angle 0.09061 degree. That gives us 55.472 ohm at an angle 69.05311 degree. And C equals to y, that is equal to 315 into 10 to the power minus 6 mho at an angle 90 degree. Taking receiving end voltage per phase as reference, we can write VR equals to 76,210 volts at an angle 0 degree. We have determined receiving end current IR equals to 154.372 ampere at an angle minus 31.7883 degree, and generalized constants for nominal T equivalent circuit A equals to D equals to 0.998125 at an angle 0.1808 degree. B equals to 55.472 ohm at an angle 69.05311 degree, and C equals to 315 into 10 to the power minus 6 mho at an angle 90 degree. Expression for sending end voltage per phase, Vs equals to A times VR plus B times IR. Using values we get 0.998125 at an angle 0.1808 degree into 76,210 at an angle 0 degree plus 55.472 at an angle 69.05311 degree into 154.372 at an angle minus 31.7883 degree. That gives us 82,881.811 plus j times 5,425.1236 volt. This may be written in polar form as 83,059.175 volt at an angle 3.745 degree. For star connected system, line to line sending end voltage, Vs line equals to √3 times Vs, that is equal to √3 into 83,059.175, which is approximately equal to 143.863 into 10 to the power 3 volts or 143.863 kilovolt. On no load, receiving end current IR equals to 0. Therefore, receiving end voltage per phase on no load VRO equals to Vs divided by A. Using values we get 83,059.175 at an angle 3.745 degree divided by 0.998125 at an angle 0.1808 degree. That gives us 83,215.204 volt at an angle 3.5642 degree. Let us now determine voltage regulation, that is equal to VRO minus VR divided by VR. Using values we get 83,215.204 minus 76,210 divided by 76,210. That gives us 0.09192 per unit or 9.192%. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to determine generalized constants A, B, C and D of a three-phase medium length transmission line based on its nominal T equivalent circuit when values of transmission line parameters are given. We have also learned how to compute percentage voltage regulation of this line using those constants when load details are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.